at the same time also learn its rank from the data. Because if you remember, I said that if you, in a real data case, you do not know the true rank of the tensor. And so this is an approach that we came up with that can both estimate the PMF tensor and also the rank from data. Okay. So this is a brief outline. We look at the motivation. Of course, this has already been covered. Also the tensor representation of a PMF. And then we look at the Bayesian model specification. And then we see how can we learn the posterior distribution. And we use a technique called variational inference. And the algorithm that we propose here is called VBPMF. Yeah? And then we look at the synthetic data results and also real data as well. So we've already heard a lot about the motivation of why we need to estimate the PMF of a set of discrete random variables. We've looked at already applications, as some of the examples are in recommender systems and data classification. And it's generally a difficult task to estimate a PMF, especially using a histogram because of the curse of dimensionality. As you increase the number of random variables, you need increasing data in order to get an accurate estimate. And so recently what has been done is to note that we can view the joint PMF as a tensor, and then to impose a low rank CPD, or canonical polyadic decomposition, in order to reduce the problem size. Yeah? So this has been done in references 1, 2, and 3, which you also saw in the previous talk. Then, as I said, the rank of the PMF is usually unknown, and generally it needs to be manually specified. Yeah? In other words, you need to do this validation where you have some candidate ranks, and then you test each one of them, and you select the one that minimizes some, some criterion. Yeah? And so there are already some model order selection techniques that exist. So we have the Akaike information criterion, which is the AIC, the BIC, which is the Bayesian information criterion, and these ones have been in existence for very long, I think since the 70s. And then we have a recent technique that was proposed in reference 4 that is called the decomposed normalized maximum likelihood approach. And these three techniques, basically what they do is that they have a compromise between how well the model fits the data and how complex the model is. Yeah? So they, as in, try to like balance the two of these considerations. Yeah? So our contribution is a Bayesian PMF estimation algorithm that estimates the PMF tensor. It learns the rank from the data, and it does not require any cross-validation. So we can actually learn the rank just by one training run over the data. Okay, so let's look at the tensor representation of a PMF. We have n random variables, x1 through xn. Each of them takes n states. And the joint PMF is represented as a tensor of dimensions I1 through In. And each location or each element of the tensor represents a joint probability of a particular index combination. And then we say that we can impose a canonical polyadic decomposition on the tensor. And we have the loading vector, which is the lambda, and the factor matrices. And so this is one example of a CPD if we have a three-way tensor, right? And we saw that this CPD is is a special kind of a CPD because the loading vector and the factor matrices have to fulfill these constraints, which are known as the probability simplex constraints. So in other words, the loading vector has to be non-negative and has to sum up to 1, and also the columns of the factor matrices have to sum up to 1 and also have to be non-negative. And then we use the same data model that we had before. So we observe a variable yn with probability 1 minus p, it's equal to xn. And if it's missing, this is with a probability p. And we want to estimate the joint PMF tensor from t observations of the random variables. So we have a data set capital Y that has all the observations. So now let's look at the Bayesian model specification. So the first thing we need to do is to specify the joint likelihood of the observations Y, and these are given by this equation here, which we saw before. And actually, this part in blue is the probability of one particular observation given the given the CPD components. And in this case, we consider the CPD components as parameters because, and we need to learn them, okay? So it's different from the maximum likelihood case where we did not consider these as parameters to be learned, but rather to be estimated. And we'll see what the difference is here. So since we have this naive Bayes representation, we can introduce some local latent variables, which we call z of t. And these variables, they have to sum up to 1, and they have only one element is equal to 1, yeah? And the rest are equal to 0. And these variables basically tell us from which component of the capital R components the observation was drawn. Yeah? So we can now write the conditional distribution of Y given Z and the factor matrices. And this is given by this equation here, and we can see the Z here, and it also appears here on this side. And then from the definition of these local latent variables, we can see that indeed the probability that one of the elements is equal to 1 is given by the value of this loading vector lambda. So we can also write it in this way as the joint distribution. And if we look at all capital T variables, then we have this expression here. Okay? So now when we combine the two of these, we now have the joint likelihood of the data given all the parameters here. So we have the CPD components there, and we have the latent variable also there, Z. And we can write it in this way when we introduce the two expressions. And if we take the log of that, then this is the log likelihood. This is a joint log likelihood of the data. Okay? Now, as I said, these CPD components, these are model parameters. And in the Bayesian, let's say, paradigm, you need to assign them some prior distributions. Yeah? And the way in which you do this is you use some information that you know about them. So, for example, in our case, we know that they have to fulfill these two constraints. They have to sum up to 1, and they have to be non-negative, right? So one, let's say, appropriate distribution that we can use is the so-called Dirichlet distribution. This is a distribution over random variables. If you have capital K random variables in this vector mu, and they fulfill this actually this simplex constraints, yeah. So they should be non-negative. They should sum up to 1. Then as in this kind of a variable can be described by a Dirichlet distribution, which is defined as shown here. It has alpha as the parameters of the distribution, and it's given by this expression. And the main, let's say, advantage of using this distribution is that depending on how you select the alpha parameters, it can control how sparse your distribution is. And this is very helpful for inferring the rank. So I have some examples here. So if you have 3 random variables, so mu1, mu2, and mu3 here, if you set alpha equal to some value less than 1, then the distribution will be very sparse. You can see that the values are all occurring along the edge of the simplex here, or at the vertices. Yeah? So if it's at the edge, it means 2 elements are equal, no, it means 1 element is equal to 0. Yeah? If it's at the vertices, it means 2 elements of these 3 variables, of this 3-dimensional vector is equal to 1. Yeah? So, and if you set alpha is equal to 1, then basically this is like having a solution that is not biased in any way. So you can get a distribution of all kinds. And if you set alpha to be greater than 1, so let's say 10, then you find that the elements of the vector will approach a uniform distribution. Okay? So this is what we use as the prior distributions of lambda and the columns of the factor matrices. So this is what we have here. This is the prior distribution of lambda, prior distribution of the column ANR of the factor matrices. And in our case, initially, we set all the alpha lambdas here to be the same, and also all the alpha NRIN to be the same, because in advance, we don't really know, we don't have any information about how they're distributed. So it's reasonable to just assume that they are all equal. Yeah? And then these are just the logs of these 2 variables here. Of these 2 distributions. So once we have the joint likelihood and the prior distributions, that's all we need. Now we see how to infer the posterior distribution of the parameters given the observations, because this is what we want to learn. What all we have is the data, and we want to learn what are the parameters. Yeah. So this is the joint distribution of the observations and the parameters. It has 2 parts. We have the log likelihood, which we've looked at before, and we have the prior distributions. Yeah. And then via Bayes' theorem, we can learn the posterior distribution. Yeah. So Bayes' theorem is usually given by this formula. The posterior is equal to the likelihood times the prior divided by the evidence. Yeah? And mathematically, this is how it looks like. Okay? And in our case, it's difficult to solve as in this equation exactly, because in the denominator we have a very high dimensional, let's say, integral. So what we want to do instead is to approximate this posterior distribution here. So we use this technique that is well established called variational inference. And what happens here is that you want to find a variational distribution Q, which approximates your posterior distribution, and this approximation serves to minimize the KLD, which we saw in the previous talk, between the true distribution and the approximate one. Okay, so this is the expression of the KLD. It consists of 2 parts. If you decompose it, we have the evidence, which is the log P of y, And we have the term here in green. It's usually referred to as the evidence lower bound, or the elbow. And why it's called like that is because we saw that the KLD is non-negative, yeah? So that, and this term here is independent of the parameters, theta. So it means if we want to minimize the KLD, all we need to do is to maximize the elbow, yeah? So indeed, our objective function will be to maximize this evidence lower bound, and that is the same as minimizing the KLD between our approximate distribution and the true distribution. Okay. So just one last detail before we go to the algorithm. Usually, you need to assume that the variational distribution Q can be factorized. So one assumption that is made is to assume that the variational distributions that govern each parameter are independent of each other. And this helps to ensure that the solution is tractable, okay? And under that assumption, then we have some expressions for, as this expression for computing the optimal variational distribution. So, and it's very easy. So as basically, for example, if you want the optimal variational distribution for lambda, yeah, you take your joint, as in joint distribution of the observations and the parameters, and then you take the expectation with respect to the variational distribution that excludes the parameter that you're looking at. Yeah? So you can see here that this Q only depends on Z and the factor matrices and not on lambda. Yeah? So once you do this operation, then you have the optimal variational distribution for lambda, and you can do this also for Z and for the factor matrices. So this is the algorithm here. So you have a data set, you put an initial rank, okay? So all we need to do as in this algorithm is to initialize it with some high rank, okay? And since we have this assumption that the joint PMF is a low rank or can assume a low rank decomposition, we can initialize it with something much higher. And one way to do this, for example, is to select the maximum rank that ensures that the CPD is identifiable. Yeah, so this is one, like the Kruskal condition. You can use that to initialize the rank, or you can also set it manually as well. And the output is the CPD estimates and the rank estimate. And then we set the prior parameters for the lambda and the factor matrices, yeah? And as we said, we ensure that for like the lambda, it should be something that is much less than 1, so that we get a sparse solution, and in that way we learn what the rank is, okay? I'll show you one animation to show this. And then basically we have these posterior updates. We do a kind of alternating update of each of the parameters we want to solve. And then we compute this evidence lower bound, and we check when it has converged. Then after that, we can estimate the CPD components, since we have their like the distributions of these. And then to find the rank, we basically look at the loading vector, and we will see that some elements will be very small, will be something like of the order of 10 to the minus 5, and the others will be larger. So basically, we delete all the rank 1 components that correspond to those lambdas, and we have our rank. So, and this algorithm was actually we presented it at the CAMSUP conference last year. So this is an animation. Let's hope it works. But what we have here is lambda. This is the lambda. In this example, the true rank is 3, but we initialize it with a rank of 10, okay? And So here we have 10 components of the loading vector lambda. This is one factor matrix, okay? These are the columns of the factor matrices. There are 10 of them initially. And, but here I've also weighted each column by the corresponding as the value of the lambda. And then here we have the evidence lower bound, which is the objective. And then here we have the evolution of the rank. So let's look at this animation. We see what happens. Is it working? No? So is this a PowerPoint or it's a PowerPoint?
You have to maybe
Escape?
remove the pointer first.
Oh yeah, maybe. Okay. Yeah. So So let's try and see.
Does what now?
No? Oh. Let's.
There you go out of the presentation board. Again, start again.
Where do we? Yeah.
Did it work before?
Yeah, it did.
Just go to the previous slide and start again.
Yeah. Okay, somehow. Oh, yeah, I tested it and it was working, but somehow. No? Okay. Maybe we can come back to it, or
Is there a play, kind of play symbol?
when it was working just when I clicked there. Yeah. Yeah, it seems something is happening, but
Yeah.
somehow it's not.
Doesn't work, yes.
Yeah. Oh, okay.
It's in the presentation.
Yeah.
I don't know if this is because of the presentation.
Yeah.
I don't know.
Okay, so
Quando ele clicasse aqui, era para aparecer. Geralmente, quando ele clica aqui, ó, carrega uma animação, mas não carrega.
something is happening, but it's not. Okay, so
compartilhar, eu acho também, como não adianta.
Okay.
it's fine. It's fine. I can
Don't know what happened.
finish up. Yeah.
Yeah, just try it once more. Just go out of the presentation.
Yeah.
I'm going to try this.
Let's see.
Yes, that's the presentation you can show.
Here we go. But we can't see it now, yeah? So it's working now?
Yeah, when you put in the presentation mode, it doesn't work.
Yeah.
But we can share maybe without
Maybe afterwards.
Afterwards, okay.
Because then you lose time.
Yeah, just go back.
Okay, so let's go back here.
Just share it afterwards.
Okay, no, so we should go to here. Okay, so let's look at the results then. Okay, so let's look at the results. So this is using simulated data. We have a five-dimensional PMF tensor, and the true rank is 5. And the initial rank here was actually 23, and this is the maximum rank for like these dimensions. This is the maximum rank in order for the CPD to be identifiable. Yeah, and then once we have the lambda, if we delete anything that is greater than, that is less than 10 to the minus 3. And we also have the P, which is a fraction of the missing data. So what we see here is VBPMF against some other classical techniques. And this is the number of observations. This is the mean estimated rank. Yeah? So you can see that the line here, this is the true rank. And as you increase the number of observations, you can see that VBPMF, even at 10 to the power 4 observations, can accurately learn the true rank of the data here. Also, if we have some missing, if P is equal to 0.3, we can also see that it learns the accurate rank with almost no overfitting. Yeah. Here we can also check the KLD between the estimated and true PMF tensors. And also we see that the performance of VB-PMF is also very good. And then in terms of the runtime, of course, because for these other techniques, you have to check all possible ranks. You know, you have to go 1, 2, 3, 4, etc. But for VB-PMF, you just estimate it, initialize it, and run the algorithm once. So you actually have some, if the size of the data set is quite large, then you can see that in terms of the runtime, we have a saving here. Yeah. We also see similar results if now the rank is 10 instead of 5, so this is a higher rank. We also have the same observations that we had before. Okay. And for real data, we also use the movie lens data set as before, but now we pick 50 movies. So we have a tensor of dimension 50, and each dimension is equal to 10. Yeah, so it's a very large tensor. In this data set, 67% of the data is missing. Yeah, so it's also very challenging. We perform 20 independent trials. We use the same metrics that we had before, so the root mean square, the root mean square error and the mean absolute error between the hidden and the true ratings, and also the negative log likelihood between the estimated and the true models. Yeah, and here we have VB-PMF here. And then we have the model order selection technique, yeah? So remember for VB-PMF, we don't need that, yeah? But for square EM PMF, we have to use one of these, yeah? So either we check the validation errors on the validation set, or we use these other techniques that already exist here. And then here we have CTF3D. This is the algorithm that uses the 3D marginals that we saw in the last talk. And this is a classical technique that is used for this movie data. Yeah? It's called biased matrix factorization. So we can see that VB-PMF has the best performance across all metrics, and the runtime in comparison is much, much lower, right? This is 3 hours. These others are 20, 59, 41, yeah? And this is because you need only one training run, yeah, and you learn the rank. Yes, so this is the performance here, and so we have presented a Bayesian PMF estimation algorithm that can automatically learn the rank. It's faster, it's robust when you have missing information. And actually, we now have an extension of this where we want to have a scalable algorithm, because if you look at these results here, actually the runtime is still increasing in a linear way to like the size of the data set. So we have also an improvement that we've been working on that doesn't grow linearly with the size of the data. So yes. Thank you for your attention, and I'm happy to answer any questions.